Hello, in this video we study differentiability and continuity. Let's record continuity. So firstly we study limits, right? We say that a function may not be continuous but may have limit at some point. After limit we consider continuity, right? And then now differentiability. Look at this. So limit, a function is continuous if the limit of f of x when x approaches x0 equal to f of x0. And of course, we need the condition that x0 is in the domain of the function, right? Is in the domain. But when you consider the limit, you don't need that. The limit of f of x when x approaches x0 may be some number. And I think we consider different examples like this. Like the typical example when we start the topic limits is x squared minus x over x minus 1 when x approaches 1, right? We know that the limit is x, but the function x squared minus x over x minus 1 is not defined at 1 because 1 is not in the domain. So the function is not continuous. And we know that there is a hole, right? There is a hole at x minus 1. The function look like this. I mean the graph. So you move from limit to continuity. You require more condition. And the condition in here is x0 is in the domain. And not only that, the limit should be equal to the function value. No. That situation, yes. And now, when you move to differentiability, that means we are talking about the existence of the derivative, right? The existence of the derivative. Again, what is the derivative? At some point, let's say at x0, we know that the derivative is f prime at x0 equal to the limit of f of x minus f of x0 divided by x minus x0 when x approaches x0. Again, derivative is defined via limits. You see? So that means we have right to consider, and not only a right, we need to consider the left limit and the right limit. The left limit and the right limit. Do you remember that? Because a limit is x if the left limit and the right limit are equal. Like this. This is the left limit and this is the right limit. If they are equal, yes, the limit is x. You see? So, we have limit, so we need to consider left limit and the right limit. And again, there are examples, a lot of examples that the function is continuous, but it's not differentiable, means the limit does not exist at that point. Okay, look at this picture before we move to more detail, right? So like you have function, it's the absolute of x. We know that the function is continuous, right? Everywhere. Because the graph is continuous, right? Okay, so this is the graph of y equal to absolute of x. Okay. Now, I'm interested in 0, point 0. Because you see the function, the graph of the function has two parts, right? One is corresponding to x greater than 0. Another one is x less than 0. You see this? So 0, and you can see 0 is some kind of, interesting point. Now I want to consider the limit. This limit, the derivative at 0. I want to see if the derivative at 0 exists or not. Okay, that is my question. So I want to find derivative at x equal to 0. That means I have to consider the limit, right? So let's write the limit. We know that f of 0 is equal to 0, right? And the limit f of x minus f of 0 over x minus 0, x approaches 0, is limit of absolute of x minus 0 divided by x minus 0, x approaches 0, and that is limit of absolute of x over x when x approaches 0. All right, now look at this. On the top you have absolute of x, right? You know, the absolute function is the absolute function is equal to x if x greater than or equal to 0, but that is negative x if x less than 0, because absolute of x is the distance from x to the origin. So when x is on the right of 0, that distance is just equal to x, right? A positive number. But when x is in the left of 0, so means x less than 0, you see, then the distance should be the negative of that value. So based on the definition of absolute function, we need to consider two cases in here, right? The first case when x approaches 0 from the left, and the second case when x approaches 0 from the right. Is that correct? When x approaches 0 from the left, we have the left limit. So the limit when x approaches 0 from the left, that is negative x over x, because absolute in that case equal to negative x. And that is negative 1, you see? And when x approaches 0 from the right, the absolute is equal to x, because x is positive, right? Then we have the right limit equal to 1, you see? So the left limit and the right limit are different. That means this limit does not exist. That means the function does not have derivative at 0. So the answer is no. The derivative does not exist at 0, given that the left derivative and the right derivative exist, because the left limit and the right limit equals. Right? So if you look at this picture, and if you remember the meaning of the derivative is the slope of the tangent line. Right? Let me write here. Derivative is the slope, right? The slope of tangent line, look at this. If you consider this point, right, from the right, so that means, you know, from this, the slope is the same, right, with this straight line. And the slope of this, since the angle is pi over 4, right, or 45 degrees, the tangent of this guy is 1. Tangent of pi over 4 is 1. You know, don't forget the tangent. The tangent of this angle is the slope of that straight line. Why? The tangent of this angle, the tangent of this angle is different. Oh my goodness. The tangent of this angle is different one. You know, because that is we need to find the slope of this guy, right? But this angle, the angle is 3 pi over 4. And tangent of 3 pi over 4 is negative 1. That's what you have in here, the left derivative. You see? And this is the right derivative, 1. That is tangent of pi over 4. And this is tangent of 3 pi over 4. So this example shows you, yes, the function may be continuous, right, at some point, but the derivative may not exist because the left limit and the right limit are not equal. Okay, so you can see the evolution, right, from limits to continuity and from continuity to differentiability. That means to the existence of the derivative. Okay, so overall, Let's make some summary in here. Derivative, we have left derivative, we have right derivative. Okay, if the left and the right derivative equal, then the function has derivative. That means derivative is x, right? Then the function is differentiable at that point. Okay, otherwise, the function is not differentiable at that point. So, what do we need from this example? In order to show that the function is differentiable, we need to consider the continuity of the function first. You see this? And then, only after that, you consider the existence of the derivative at that point. So, I need two conditions, right, for differentiability. Right here. The first condition, the function should be continuous. The second one, the derivative is x. All right, so if you check two conditions and two conditions are fulfilled, your function is differentiable at that point. Okay. Now let's consider the differentiability of the function fx equal to x to 1/3 or x cubed at x equal to 0. Okay, so we see that the function is continuous. Okay, yeah, the first condition, the function f of x equal to cube root of x is continuous at x equal to 0, because the function is defined as 0 and the function value at 0 is 0. That is the limit of the function, right, at 0. Now we need to consider the derivative. Okay, derivative. So we have, let's say, f prime at 0 if as x, right, I write here if as x should be equal to limit of what? F of x minus f of 0 over x minus 0. X approaches 0. Okay, so f of 0 is 0 because you plug 0 into the function, you get 0. So this is the limit of cube root of x over x when x approaches 0. You might simplify x, you get 1 over x 1 minus 1/3, right, when x approaches 0, or that is limit of 1 over square root of, no, that is cube root of x squared when x approaches 0. Since you have x squared in here, when x approaches 0 from the left or from the right, 1 over x squared approaches positive infinity. So when you apply cube root, right, to this, the limit is also infinity. Let me write it down, right? X approaches 0, and here I can write cube root of 1 over x squared. Okay, since this guy approaches positive infinity, as x approaches 0, you apply cube root, the limit is still positive infinity. So it says, yes, the limit is x and equal to positive infinity. Okay, so here at this point, if we are talking about differentiability from the point of view of the existence of the derivative, and we didn't say anything about the finiteness of that derivative, then the derivative is x at this, right, at this point and equal to infinity. Or in that case, the slope is infinity. So what does it mean? The derivative is x and equal to positive infinity. That means the slope of the tangent line to the graph at x equal to 0 is infinity, right? All right, so what is that? You know that the slope, right, of the tangent line is the tangent of the angle between that line and the x-axis. Is that correct? So if you remember the unit circle, and we have the tangent a6 in here. Here is positive infinity, here is negative infinity of tangent. So if you have some x in here, you connect x with the origin. That is the tangent of x. You see, if the tangent of x approaches positive infinity, x should approach where? Pi over 2. You see this? Pi over 2. So, approach pi over 2, okay? So, that means, in this case, of course, we know that tangent is not defined at pi over 2, at negative pi over 2. We know that tangent x is not defined, right? At positive and negative pi over 2 and plus k pi. So, when the derivative is infinity, that tangent line look like this. That tangent line look like this. You see, because the angle will be pi over 2, right? Because the angle will be pi over 2 in here. So if you look at the graph of the function y equal to cube root of x, you see the following one. Of course, you want to graph this function, right? And we know that the graph of this function is symmetric with respect to the graph, symmetric to the graph of x cubed with respect to the y equal to the x, right? Because they are inverse of each other. So if we graph those functions, we have the following picture. You have x in here and y in here. And the graph of x cubed, how to find that? Let me x cubed, so when x equal to 0, we have 0. X equal to 1, we have 1. X equal to 2, we have 8, somewhere over there. So that is the graph of x cubed, okay? All right, so this is x cubed. Then you need to make the symmetric one, right? So this is my straight line y equal to x. The graph of cubic cube root of x is symmetric with respect to the graph of x cubed. Symmetric to the graph of x cubed with respect to the y equal to x. So I have the following one. Let me write. It should look like this. Passing through this, and then symmetric, and then symmetric in here, and then pass right here. Okay. So this is graph of cube root, and you can see that actually in this case, the tangent line at x equal to 0 is this. This is the tangent line. So in order to finish this video, let's consider this example, the piecewise function. F of x equal to x cubed minus 3x squared plus 3x when x less than or equal to 1, and x squared minus 2x when x greater than 1. So you can see the function actually has two parts, right? The part is corresponding to x less than or equal to 1 is right here. That is the cubic. And another one is this. So we consider differentiability of this function at x equal to 1. That means we consider smoothness, right? The smoothness. Sometimes you can hear that. The smoothness. That means, the function is smooth at that point or not. Remember the function absolute of x, right? Look like this. We saw that the function is not the derivative does not exist at x equal to 0, because it seems like when x equal to 0, here you see some angle, right? So the graph is not very smooth. Does that make sense? Smooth look like this, right? But the graph of x of absolute of x at x is 0 is not smooth. So, differentiability means like smoothness, okay? All right, so again, we see that we need to consider continuity of the function first. So, continuity, we need to consider the limit of the function at x x approaches 1. And of course, in this case, you need to consider the left limit and the right limit, right? So let's see the left limit. What is the left limit? In order to see the left limit, we need to take the part for x less than or equal to 1, right? So that is limit of x cubed minus 3x squared plus 3x when x approaches 1 from the left. So you just plug 1 into this function, right? You get 1 minus 3 plus 3, which is 1. And then you consider the right limit. But for the right, you need to pick another one, right? X squared minus 2x. So limit of x squared minus 2x, x approaches 1 from the right. Again, you plug 1 into the function, you get 1 minus 2, which is negative 1. Interesting. That means, the function is not even continuous at this point. So the left limit and the right limit are different. The limit at 1 does not exist. So there's nothing to do with this. That means, the function is not differentiable because, not continuous. Right? Let me change the function a little bit, okay? Let me change the function a little bit. So I would change as follows. F of x equal to x cubed minus 3x squared plus 3x when x approaches less than or equal to 1, and 2x minus x squared when x greater than 1. Then if we change this, we see that the left limit at 0, at 1, right? At 1 is equal to 1 minus 3 plus 3, which is 1. While the right limit is 2 minus 1, which is 1. Perfect. So the left limit and the right limit equal. The function has limit at 1, and that is 1, right? And the limit is 1 at the same time. The function is defined at 1 because x less than or equal to 1, right? And the function value at 1 is the left limit. So this is equal to f of 1. That means the function is continuous at x equal to 1, right? And now we have right to consider the differentiability. Then we need to consider the left limit and the left derivative and the right derivative. Okay, so we need to consider the left derivative. So we need to consider the limit of f of x minus f1 over x minus 1 when x approaches 1 from the left, right? And the right derivative, that is the limit of f of x minus f of 1, x minus 1 when x approaches 1 from the right. Of course, f of x in here, when you plug the function into these limits, you need to pick different one, right? Because for the left you have x cubed minus 3x squared plus 3, but for the right you have 2x minus x squared. So you have different functions in here. Let me write it down, and then we'll see if we can solve that or not, okay? Because it is pretty long. So this is the limit of what? Of x cubed minus 3x squared plus 3x minus 1, because f of 1 is 1, right? over x minus 1 when x approaches 1 from the left. And this one is limit of 2x minus x squared minus 1 over x minus 1 when x approaches 1 from the right. You see? So we have, this is our left limit and right limit. So we need to consider this. You know, again, right, we need to use factorization. Okay, why? Because when you plug 1 into each limit, you have 0 over 0. That means 1 is the common 0 for both, right? For this, and for x minus 1. So you can factor, okay? Let's do this. For the first limit, I write limit when x approach 1 from the left. And here I have x minus 1. I factor the top. I have x minus 1 in here. Okay. So you may do long division, but you know, I do that right away in here. I have x squared because we have x cubed, right? We have x right here already. So I have x squared. I need x squared in here. And then I multiply x squared back here. I get negative x squared, but I have negative 3x squared, right? So I would need negative 2x. Why? Because when I multiply negative 2x with the x, I have negative 2x squared. With negative x squared, we have right here, so we have negative 3x squared. Agree? And then once we finish with, you know, the polynomial of degree 1, we move to free coefficient. We have negative 1 in here, negative 1 in here. That means in here we have plus 1. Okay? So this is equal to the limit of x squared minus 2x plus 1 when x approaches 1 from the left, because I already simplify x minus 1 with x minus 1. And now I just plug 1 into this function. I get 1 minus 2 plus 1, which is 0. Okay, perfect. That is my left limit. Now let's do almost the same thing for the right limit. So I factor the top. I get x minus 1. Okay, and here I have negative x squared. That means here I have negative x, and the free coefficient is 1. Okay, and then you have x minus 1 when x approaches 1 from the right. Look at this. Yes. So now you simplify x minus 1 and x minus 1, right? You get limit of negative x plus 1. X approaches 1 from the right. And again, you plug 1 into this, you get negative 1 plus 1 is 0. You see? The left derivative and the right derivative are equal. Perfect. That means the derivative exists, right, at 0. I write like this. F derivative at 0 is x and equals 0. So the function is differentiable at x equal to 0. That means the graph of the function is smooth at x equal to 0. Okay, so I hope that the video is clear enough. And again, right, we need to remember the picture at the beginning. Limit, continuity, and differentiability. The function is continuous if the limit exists and equal to the function value. The function is differentiable if the function is continuous and the derivative exists. Okay, so I stop my video in here. If you have any questions, please feel free to let me know. Thank you.